Well, welcome to another RDWorks Learning Lab. I'm afraid we're going to rattle on with the same old subject that we've been checking out for the past few sessions, and that is trying to track down where these vertical lines are coming from when we do 3D engraving. The first set of tests I did seemed to blame the stepper motor, resonance in the stepper motor system. The second set of tests that I did seemed to clear the stepper motor and say it's something to do with the laser beam itself and the pulsing laser. One of the responses that I had back was maybe I would like to check out the Eagle 3D engraving that I did, because that particular correspondent couldn't see any differences when he changed the speed. That would seem to indicate that the problem is back blaming the stepper motor. I've not run that test on acrylic, and acrylic is the best telltale that you can possibly get for checking out the laser. It tells you its power, what's happening. It's much better than high-speed photography. So what we're going to do first of all is we're going to run the Eagle test, and I'm going to run it in several different ways, and I'll explain as I go through and do each one. Now, I've reconfigured my machine so that it's now operating in a scan mode called special mode. I've got no idea what it does, other than the fact that it does say in the book that it's something to do with high pulsing, high frequency and high pulses to give you a better flat bottom. Now, this first run that we're going to do is at 50 millimeters a second. I've got the minimum set to 8% and the maximum power set to 50%. So I'm going to get quite a deep cut during this first run. Now, the other thing that I'm doing, I'm putting some of my neodymium magnets here so that there's no chance that the sheet is going to move, because I'm going to run 2 or 3 times over the same pattern, and I definitely don't want the sheet to move between patterns. We're doing something called a unidirectional sweep, which means it's only cutting in one direction. We'll come back later when this first run is complete. Okay, well, there's the first run, and I think you can see very clearly, without going in close, how much of a canvas effect I've got in the background. It's a definite exaggeration of what I saw when we cut it in wood. Now, at the moment there is a little bit of a software glitch of some sort in the file transfer across here, but I'm not going to worry about that. What we are now going to do is going to run it again, and we're going to run it at 220 millimeters a second, and we're going to drop the power to 30% because I don't want to cut it too deep. I just want to take another skim off the top. So 8% and 30%. Right, we're going to stop the program at that point. So that we can compare the first part of the program with the second part of the program. And I think even from a distance we can see that even though I'm running at some strange number, and I purposely made that 220 millimeters a second so that it wasn't anything to do with 50 millimeters a second, like 50, 100, 150, 200, 250, where there's a possibility that something could overlay the pattern that was already there because it was a multiple of. So 220 is definitely not a multiple of 50, but looking at it from where I am, and you may not be able to see that, but we'll look at it closer later, all the lines seem to be perfectly aligned. There is no significant difference. So I'm going to try one more thing now, and this is something that I haven't tried before. I'm going to try and burnish that picture by putting heat onto it rather than cut it. And I'm also going to put the speed right down as well, because the speed is the thing that we need. We need a very low speed so that we can heat the surface up locally rather than cut it. We're trying to burnish the surface. We'll leave the minimum power at 8%, and we'll put the maximum power down to just above that strange pre-ionization stage, which is 14%. And then I've got to do one other thing. I've got to drop the focus down. so that I haven't got the same energy density, and hopefully that will polish the surface. Now whether or not that will work, we shall have to try. Now if this technique is working, then obviously it will only work for acrylic, because acrylic's the only material that you can basically flame polish. Okay, well we'll stop that there. And even though we have sort of flame burnished this, it's certainly a lot better than the debris that's been left on the surface after these first two runs. We probably haven't done it quite enough because we haven't got a shiny finish yet, so the parameters aren't quite right, but it does show clearly again that we've got these vertical stripes that line up on all three of these different speeds, 20, 220 and 50 millimeters a second. So my correspondent that wrote saying couldn't see any difference in the speeds was perfectly right. Now that leaves me with a big problem, because that immediately begins to tell me that we are back with something which has got to be linked up with the movement of the head, and the only thing that can be linked up with the movement of the head is actually the stepper motor or the belt. Let me take a little bit of a closer look now at the details of this belt and stepper motor drive system. Before we go on to any more tests, I've just measured the diameter of the pulley, the drive pulley here for the stepper motor, and basically it's 17.2 millimeters across the outside of the belt. What I've also done is measured the thickness of the tooth there, because what I'm trying to establish is the outside diameter of the pulley, and I can't obviously get to the pulley because it's got the belt round it. But by doubling that thickness there, I get to 2.6 millimeters, which is for both sides. I can then subtract that from the outside dimension of the pulley, so I've got 17.2 over the belt minus 2.6 should give me an outside pulley diameter of about 14.6. Now I've also checked and found that there are 16 teeth on that pulley. So with 16 teeth and an approximate outside diameter, I should be able to look up on a standard pulley chart, and although you might not be able to see that clearly, we found something here with 16 teeth on it, which has got an outside diameter of 14.52. Now 14.52 is not far off of my 14.6, so I think we've found the right pulley here. It tells me that it's got an effective diameter of 15.28 millimeters. Now 15.28 millimeters is basically the drive diameter. So if we take the pitch circle diameter and multiply it by pi, then we finish up with basically 48 millimeters, and that is the circumference of the effective driving diameter. Now this standard stepper motor has got 200 steps per rev, and if I divide the 48 millimeters that we've got by 200 steps, then what it means is I've got a dimension of 0.24 of a millimeter for every step of the stepper motor. Now in reality, I've checked the switch settings on my stepper motor drive, and I've found out that it's actually times 10. So it's a micro stepping system, and it's got 2000 steps per rev, not 200 steps per rev. And that basically means that we've then got 0.024 of a millimeter per step. Now, one of these two dimensions is what I'm really looking to match up with that pattern that's on the job there. So we're going to check that out later, but first of all we're going to do one or two more tests, and we're going to take a look at the edge of some more grayscale tests. So I've got the grayscale set up to 8% power and 50% power, and I've got the speed set to 50 millimeters a second. But in addition to that, if you remember, against the power window there is an advanced button, And in that advanced button there is a frequency, which has always puzzled me, and it still puzzles me today. But what I have done, just in case this special mode that I'm running the machine in at the moment has some sort of effect for this frequency, I've built in a frequency of 5 kilohertz to this program. So we're running special mode, 5 kilohertz, 50 millimeters a second, 8% power and 50% power. We'll see what happens. Now, for comparison purposes, I'm going to run the same test again, but this time we're going to run it at 150 millimeters. Now, the thing that's always puzzled me about this test is that where the stepper motor starts from the left-hand end, there's always a sort of a strange kick in the first groove, but that kick is never in the second and third grooves. That tends to point the finger back towards the stepper motor. Right, I've now set the program back to 50 millimeters a second, exactly the same as the first one there. And I'm now going to do something a little bit different. In fact, I exaggerate. I'm going to do something a lot different. What I have here is a block of steel. It weighs almost a kilogram. And I'm trying to very carefully place it in a position where it doesn't distort the head in any way to offset or cause the beam to be picked up on the mirror in the wrong position. The strongest position is with the bearing across here this way. So what I'm going to try and do is to mount this piece of material, if I can. Right. Now I've clamped that piece of material on there now. So that head is now carrying an extra kilogram of mass. That should truly either upset the acceleration and the deceleration, and it should also, if it's going to do anything, it will probably, although once it's up to speed, it won't affect the top speed once it's accelerated, but if there's any sort of micro vibrations in there, it will probably help to dampen out some of the micro vibrations. Hoping that it doesn't all fall apart, let's give it a try. Okay, let's go and examine these results and see if we can get any clues as to what's really going on. Does this get us any closer to the real truth? Now this section at the top here was done at 50 millimeters a second, and you've only got to look down here across this interface where the bottom section was done at 150 millimeters a second, and you'll find that there's continuity of these lines right the way across wherever you look. I have to say that I can't see now how that can be a laser problem. It's something which is fixed in the machine, and the only thing that's fixed in the machine is the stepper motor and the belt. And here we are now looking at the other interface, where this one was done at 150 millimeters a second, and this one was done at 20 millimeters a second. Now you've only got to look down here and you can see that line continuing down there. You can see all of these lines, although it's coarser because it hasn't got all the detail in it, the basic shape of these rows is still the same. To be honest, it does look as though there are two factors playing here. We can't see it on this picture, but we'll go and look at the other tests that we did to see just what I mean. Now this is our 50 millimeters a second test, and I think you can see that if we look down on that pattern,
there are definitely striations across there, but that's like a harmonic, because if I turn the pattern round and we look at the side where the laser beam is cut in, you'll see that there are a lot more marks on the side wall than there are on the bottom. First of all, we've got our huge set of gear teeth here. Whatever causes those, we'll have to investigate that, because I thought it was the laser turning on and off and settling down that gave that effect, but I'm going to have to rethink that now, because as I said, I was never completely sure why, if that was the case, it doesn't happen on the second groove. And you can clearly see on that second groove there's a lovely pattern along there, but it's not the same pattern that's occurring on the back face. I think you can see, if I turn that through to the light, there's a lot more going on than that obvious pattern. There are at least 1, 2, 3, 1, 2, 3, 1, 2, 3. There are at least 4 smaller elements to every one of those patterns. So let's just check what the striations are on that back face. Now, even with our SP mode, when we run 3 times faster, we get this strange start condition, which is a lot slower than this one. And this is the thing that fools me into thinking that it's something to do with the laser, because if the laser was trying to go up and down in its pulse, and this was going a lot faster, then the pulses would stretch out. Okay, I've just made a case for it being the laser, because I couldn't understand how the stepper motor would start off in a very lumpy manner. It was a bit of a struggle, but with my graticule I managed to measure the number of striations along the edge of these slots, and here's the results that I came up with. So after losing count and patience many times, I eventually managed to finish up counting 41 and confirming 41 striations in a 10mm length. So if we divide the 10mm by 41, effectively it gives us 0.244mm per striation or pulse. That's an interestingly familiar sort of number. So now that we can lay these two figures together, I think you can clearly see that 0.24 and 0.244, give or take a little bit of my measurement error, are one and the same figure. And that figure is in fact the distance moved by the stepper motor in its raw 200 step state, not in its micro stepping state. So basically what I'm holding here with these pieces of acrylic are the same as footprints in the sand. We've got a permanent record of what power and speed the laser was doing. It's a bit like, as I said, footprints in the sand. You can see which direction somebody's travelling. You can work out whether they're running or not. You can work out approximately what their weight is, but you can't tell what colour hair they've got or how big their nose is. So there's a limit to what we can deduce from this information. But there are some fairly simple deductions now that begin to make sense. Let's just take a quick look at this picture. Now, if I assume that the laser beam is moving steadily across here, and all of a sudden it switches on and carries on at a steady speed and switches off, so in other words it switches on, off. As it's on, it cuts a furrow which is a uniform depth, because the power is uniformly distributed over that area. Now if I travel at 3 times the speed, on, off, and I'm using the same power, then what happens is the depth of cut is less. So the depth of cut shows us the power that's being applied to any point along its travel. So there's a speed and power relationship in these two first pictures. So what happens when I see a picture like this? Well, we can obviously deduce that this last piece here is running at a steady speed. But we can also deduce that if this is where the laser beam started, then at that point we've got power which is held in a certain position. And as it's held in that position, it burns deeper and deeper and deeper. But as soon as it starts to move off, its depth of cut is proportional to its speed. 50 millimeters a second, 150 millimeters a second, deep, shallow. So it gets shallower as the speed increases, provided the laser beam is at a fixed power. So that's what this picture shows us. We can deduce that the laser beam was on here and standing still, nearly, to get this depth of cut. And so when we see a picture like this, which is what we see at the beginning of our cuts, it clearly means that the stepper motor, as it starts off, is not moving at a steady rate. It's jumping in lumps, lumps before it gets to a steady state. So that's interesting point number one. I thought that the stepper motor would move off very smoothly and fast, but it seems as though it's jumping in probably 4-step divisions, because these pulses are so far apart that they must be being commanded to do something at the beginning. Now, I don't know how they program stepper motors. I understand the principle of stepper motors and I know approximately how they work, but I've got no idea how they actually program the stepper motor to accelerate to a best maximum speed, and then how its deceleration takes place. But what we can deduce, like footprints in the sand now, is exactly what is going on, and this is the acceleration mode for the stepper motor. It's obviously stepping forward, the laser beam switches on and it's not moving, then it starts to move, and as it moves fairly quickly the depth of cut decreases, but then it stops after 1, 2, 3 or 4 steps, whatever it's doing, and then the power stays the same but the depth of cut gets deeper, and then it moves off to another one, and so it goes, and eventually we get to a point where we're moving at a steady speed and the laser beam is now ploughing a nice even furrow. I say even, relatively even, because in the bottom of this furrow there are all sorts of little imperfections. So when you look at this from above, what you really see are these ripples, and that gives a very wrong impression of what's going on, because these are some sort of harmonic motion that's going on, but buried inside that there are lots and lots and lots of smaller imperfections, and these imperfections are in fact equivalent to 1 step stroke. It's a 200th of a rev, which equals 0.24 millimeters. And these little items are, if we could draw it backwards to see the shape of these teeth, then you would find that yes, they are randomish, but they seem to form this amazing pattern, and that's what's confusing. There are lots of randomnesses in there, but there's this pattern as well, but that pattern is based on 1/200th of a rev, 0.24 millimeters. So because this 200th of a rev is such a dominating feature in the patterns, one has to assume that to get the speed up, they operate again with this 200th of a step. Somewhere here they're using 1 step to drive, not 2,000 steps to drive and accelerate. And once they're up to speed, again, it's a bit like moving into top gear. They use the 200 steps to drive the motor at a steady speed. But only when they want to accurately position the motor do they switch down into first gear to very accurately creep up to the correct position. So that looks as though that's how this system works. And looking at several of these patterns, from what I can see, this waviness, this harmonic that's in there, seems to be made up of 4 steps, approximately 1 millimeter. So it's 1 millimeter, which equals this very coarse vertical line system. That's what you can see, even though built into that there are 4 other smaller steps. And then finally, just to verify that what we are seeing is stepper motor problems, and no longer we're looking for lacer problems, because this is the mechanism by which we're generating this shape that fooled me. So I'm sure you'll be interested to know what happened when I added a kilogram weight to the head. Well, the bottom trace is the answer to that question. This is the difference between 50 millimeters a second without the weight and 50 millimeters a second with the weight. And as you can see, the stepper motor has struggled to accelerate over a much longer period. And once it has accelerated, you'll notice the difference in the surface finish between the top trace and the bottom trace. There's much more of a pattern, which is the 4-step pattern that's occurring on that bottom trace. So now that we understand where these marks are coming from, what we've got to try and do is realise, is there any way that we can mitigate those marks? That's something I'm going to have to think about for the next session. Thanks for watching.